association with the newly formed Indian Institute of Metal Students Chapter at NIT Durgapur. And today's talk is the second in the series of 4 such. When we have planned to conduct 2 more such programs when renowned professors, researchers from the leading foreign universities will deliver lectures on their area of research interest. I would thank our institute authorities, our director, our registrar, the deans, and all functionaries of IIM Kolkata for extending their support to organize this program. And my heartfelt thanks, my sincere thanks to the coordinator, my colleague Dr. Arup Kumar Mondol, for his effort to organize this program. This kind of functions will enlighten our department and our institute as a whole. We have conducted several such programs, 1-day program, 2-day program, 5 days short-term programs, short-term courses, seminars, etc. So now, because of the pandemic situation, we cannot conduct this in physical mode, but we have to adopt this on virtual mode. So the last 6 months, when the pandemic started, we are organizing the functions like this, the webinar, when the professors, the academicians, the researchers from well-known R&D organizations, the industry professionals are being invited to give lecture in their own area of interest or area of research. So what I feel that this kind of functions will benefit the department, the participants, and as well as it will make the networking between different organizations and institutes. That is very much essential for any engineering studies, particularly our department like ours. Our department is really privileged to interact with renowned professors, researchers, and industry professionals from all around the globe using this platform. The earlier talks were mostly on structural materials. The talks that we have conducted so far were mostly on structural materials like steel or advanced structural materials, etc. Today's talk is on magnetic materials, which Dr. Varun will be delivering, and which is, magnetic materials is a very important functional material. So it's a different kind of material. Materials can be structural, it can be functional. So most of the earlier talks are on structural materials, but today's talk is entirely on the functional, a particular special type of functional material, that is the magnetic material. Very important so far as the electronic components or electronic industries are concerned. So I must thank Dr. Chaudhury for accepting my invitation to deliver a lecture on his area. On behalf of the whole Metallurgical Materials Engineering family of NIT Durgapur, and on my personal behalf, I express a warm and hearty welcome to Dr. Chaudhury and also all the participants in this online interaction session. The participants list is quite long. From the last report obtained from the coordinator, this webinar has been registered by more than 250 participants, including our own students, scholars, participants from foreign countries all around the globe. My heartfelt thanks to all the participants for their interest, and I could cordially invite them all to attend our subsequent webinars. This type of response really inspired us to organize more and more such talks. I hope today's webinar will be enjoyable to all of you, and the participants will be immensely benefited. I wish all success of this program. Thank you. Thank you all.
Thanks a lot.
Thank you, sir. Thank you so much.
Thanks a lot for your for your delightful word, sir, about our departmental activities and being tender towards us. Finally, we move on to today's technical session, which we all are were eagerly waiting for. We are extremely glad and grateful to have Dr. Varun Chaudhury grace this occasion with his presence. The topic of his talk today is accelerated development of high performance magnetic materials for emerging technologies. Dr. Varun Chaudhury is a postdoctoral research fellow in School of Materials Science and Engineering at Nanyang Technological University at Singapore. He had done his bachelor's and master's in physics from Chaudhary Charan Singh University, Meerut. Later, he pursued his MTech degree from IIT Kanpur in the Department of Material Science and Engineering. He had previously worked also in Rolls-Royce in NTU Corporate Lab, Singapore, School of Physical and Mathematical Science, NTU, Singapore, as a research fellow. Dr. Chaudhury worked on self-pumping magnetic cooling, magnetic materials including magnetocaloric materials, soft magnetic materials, permanent magnets, high entropy alloys, nanostructured materials for spintonics and hard disk media, magnetic nanoparticles and permanent magnet for energy application, and additive manufacturing of multifunctional materials and biomaterials, etc. He is not only a research scholar but also a good mentor. He guided a lot of BE and PhD students also. He also hold a well distinguishable position of International Advisory Board member, International Conference of Future Trends in Materials and Mechanical Engineering, India 2020, and Assistant Chairperson in IEEE Magnetic Symposium, Singapore Chapter 2018, etc. He has a joint patent with R.V. Ramanujan on self-pumping magnetic cooling. He has written the chapter in Encyclopedia of Nanoscience and Technology named as Magnetic Nanoparticle Synthesis, Functionalization and Application, and published in many popular journals like Progress in Material Science, Crypto Materialia. It is impossible to describe his achievements during his professional career and contributions to our society through the field of materials in words. So, without any further delay, I would like to invite our honorable guest speaker, Dr. Chaudhury, to share his words to us. Please, sir.
Thank you very much. Thanks a lot for a nice introduction. Let me first close my video so that we can increase the bandwidth and share my slides. Are my slides are visible?
Yes, visible.
Okay. Hello, everyone. Thank you very much. Thanks a lot. And first of all, I would like to thank Professor M.M. Ghosh for inviting me to present my work here at a very good platform where so many participants at the same time. And today my talk will be focused on accelerated development of high performance magnetic materials for emerging applications. So here are the outline of my talk. First, we will start. My talk is divided into two parts. In first part, we'll discuss on accelerated magnetic material development, especially soft magnetic materials, and in which I'll cover the motivation why we need the accelerated development and the possible high throughput techniques to develop the magnetic materials, the use of additive manufacturing for developing the magnetic materials, and our recent results on iron nickel based alloys, graded cobalt iron and graded nickel iron alloys, and then ternary system of iron cobalt nickel, and then magnetic high entropy alloys, etc. In the second half of my talk, I'll discuss on magnetic cooling, why we need the magnetic cooling and prototype designing and the performances. So the soft magnetic materials are critical to the performance of electric machines, transformers, generators, etc. They are heavily used in our daily life and even in power electronic converters, electric vehicles, wind turbines, etc. They play a vital role in clean energy applications. For an example, around 65% of United States electric energy is consumed by motorized applications. The situation is not much different if we see the global scenario. Therefore, there is an urgent need for superior magnetic component for advanced electric machines. So here are the key requirements to use the soft magnetic materials in advanced electric machines. And the material requirement is that the material should have a magnetically soft, it should have a high strength and the high value of resistivity. When I say the magnetically soft, it means that it should be easily magnetized and demagnetized. It should have a high saturation magnetization and low value of coercivity. And if you want to use this kind of machines at high temperature, then the higher Curie temperature is also required. So the relevant soft magnetic materials need a combination of magnetic, electric, and mechanical properties. So now what's the challenges to achieve those properties? Here, the first window shows the typical magnetic materials performance, the saturation magnetization, and the coercivity. A material which has a high value of saturation magnetization also has a high value of coercivity. If you want to decrease the coercivity, the saturation magnetization also decrease. So we need a material which has a high saturation magnetization and low value of coercivity, somewhere in this region. Another challenge is that when we increase the strength of the material, the coercivity also increase. So this is because they both coercivity as well as strength are the function of microstructure, and therefore it's very difficult to get a material with high strength and low coercivity. The same in the case of resistivity. If we increase the resistivity, the saturation magnetization decrease. So why we need the high resistivity? This resistivity is indirectly proportional to the eddy current loss. So we want to decrease the eddy current loss and therefore the total power loss in the electric machines. So this is a very messy engineering problem and can be solved by using AI and ML kind of approaches. However, the difficulty for that is that we don't have enough amount of database. For using this kind of approach, we need a huge database, then only we can utilize this AI and ML. So rapid development along with AI and ML can give us a best combination of required properties to use these kind of materials in advanced electric machines. So another requirement is that there should be a special variation in magnetic and mechanical properties under the component what we have inside the motor. You see here is the flux density distribution, and this is the power loss distribution. So we need a material which has a high strength, low coercivity, and also a optimum graded properties to improve the performance. So here, basically, as we all know, that the conventional technique is slow and costly. It takes around 20 years from the laboratory to commercialization. And it's very challenging to get a material with, for example, soap, which has soft magnetic properties, high strength, and high resistivity, and close to impossible to get a graded material using these conventional methods. As an example, arc melting and melt spinning, these techniques what we use in the laboratory take 1 to 2 hours to print to have one sample. On the other hand, the high throughput approaches, we can quickly measure the big composition space and therefore possibility to get a optimum composition for the properties what we want. And there is a possibility to get a graded material using such techniques. So for example, metal additive manufacturing, in 2 hours, we can print many compositions. So the goal of this study, what I'm presenting here, is that to develop a soft magnetic material with high mechanical strength, low magnetic coercivity by combining the high throughput synthesis, high throughput characterization techniques, and AI approach. These are the combinatorial approaches for alloy development. I have listed listed here all possible techniques. So we can have a discrete library or we can have a continuous library. All these techniques have their own advantages and disadvantages. For example, this additive manufacturing, we can print a bulk sample. And in case of co-sputtering, this is only suitable for thin film kind of sample. The third one is rapid alloy prototyping. This is limited that we can only have few composition at one time. Another is the diffusion multiples. This is again very time taking. It takes sometimes weeks and months to get a diffusion, proper diffusion. So here we are working on first two techniques, and today I'll present the results on only on additive manufacturing. So let's discuss how the additive manufacturing is suitable to print graded samples. We are using lens engineered net shaping, so-called lens technique to have this kind of sample. So this is the schematic here. We have a multiple powder feeder, and by changing the feeding ratio, we can change the composition. This powder comes through the nozzle and it's melted by the laser. And if we, by changing the ratio, we can either print a continuous change from the bottom to top, or we can print a discrete change. It depends on the programming you do. So here is a short video. It will show how this works. So it's basically print line by line and layer by layer. In principle, every layer can be a single composition. However, having the limitation of characterization technique, we prefer to have a few layers for one composition and then change the composition by changing the feeding ratio. So this lens technique is suitable for rapid testing of composition space. It also suitable for the graded magnetic alloy, which is required for next generation electric machines. This lens technique has several process parameters, and by tuning these process parameters, we can tune the final product property. For example, laser power, travel speed, hatch width, and lane spacing. And these all affect the final product properties. Powder parameters also affect the final product properties. So we should, for some powder, a particular powder size distribution is required. If you want to switch to another materials, it may be a different size distribution requirement. So before moving to the graded sample, we started with the model iron nickel soft magnetic materials, which is commercially available, this kind of material, using different process parameter to see the effect of process parameter on the final product. Here the phase diagram, and this particular composition has gamma phase at high temperature and alpha plus gamma phase at lower temperature, room temperature. These are the results, X-ray diffraction pattern for all these samples prepared for all these process parameters. And we found that when the travel speed is less, the sample shows a face-centered cubic structure, which is converted to the BCC-dominated structure when we increase the travel speed. Same in this another set of experiment when we increase the power and change the speed. So we can utilize, we can increase the travel speed, and then we can convert the crystal structure from FCC to FCC plus BCC and then BCC. Here are the results for that. And yes, by changing the process parameter and therefore the crystal structure, we found a significant change in the magnetic properties for face-centered cubic structure, so the lower saturation magnetization, and body-centered cubic structure is higher saturation magnetization. So by tuning the process parameter, we can tune the magnetic properties. Let's move to the graded binary alloys, iron nickel and iron cobalt. So this is one sample. In one side, it is having iron 22 nickel, and in another side, it iron 68 nickel. So as you can see here, for a higher nickel side, we have a pure face-centered cubic structure, but at the lower nickel side, we have a mixed phase. The second phase of BCC can be seen by this second peak here. Here is the magnetic properties along with the weaker hardness for all these samples. So if you see that we have a good saturation magnetization, low coercivity value, but the weaker hardness is not good for that particular composition. So we need to kind of compromise. Either we should only have a good magnetic properties, but bad mechanical properties, or the other way around. So as I mentioned in my introduction slides, that it's very challenging to get these in one sample, having both good magnetic and good mechanical properties. Then we come to the iron cobalt system. Here the crystal structure for all these composition changing from iron 30 to iron 70, having a body-centered cubic structure, and the grain size is equal or less than 100 millimeter. The magnetic properties for this sample, the saturation magnetization increase with increasing the iron content. However, the coercivity first increase and then decrease. From here, we can conclude that this particular composition is having high saturation magnetization and low value of coercivity. What is our requirement? Then we measure the mechanical property. So mechanical property for that particular composition is not good. The mechanical property is good for another composition. Then we annealed this sample, all these samples, and found that the significant decrease in the coercivity, some improvement in the mechanical property, basically in hardness. And finally, we identify a composition which is having good saturation magnetization, low coercivity, and high value of weaker hardness. So we have found a composition which is having the best combination of saturation magnetization, coercivity, and weaker hardness. Now let's move to the ternary alloy system, iron, cobalt, nickel. In this case, we have 11 composition changing from iron 15 cobalt to iron 25 nickel. It's the composition on atomic percent base is written in this table. And again, we check the crystal structure of all these samples. I would like to mention here that these all X-ray diffraction pattern we try to do in automated way. So our main goal here is to reduce the time. So all these samples, we have X-ray diffraction technique in school. So we can just load the sample and it can switch after 2 mm distance. After doing one scan, it can switch to another point and the third point. So for nickel-rich side, we have body-centered cubic plus face-centered cubic structure, while the cobalt-rich side, we have, in this side, we have body-centered cubic structure. So this is, we can say that nickel is a face-centered cubic stabilizer in this system. And here the magnetic and mechanical properties for these cells, such as contour graph for saturation magnetization, coercivity, and then we got hardness. You see, I would like to again mention here that we need a material with high saturation magnetization, low coercivity, and high value of hardness. And we were able to find this space here that we have high saturation magnetization, low coercivity, and high hardness. Currently, we are exploring the other region of this triangle so that we can find a global optimum space. Here, we tabulated all these results along with the phase, magnetic properties, and Curie temperature. So this is the composition which shows optimum magnetic and mechanical properties. Iron with 7.4 cobalt and 11.3 nickel. Now let's move to the magnetic high entropy alloys. So as you all know that this high entropy alloy is relatively new field, and lots of work has been done since 2004. So this is known now that high entropy kind of alloy, which has a combination of multiple principal elements, shows excellent strength as well as a good corrosion resistance. But for magnetic properties, only few limited literatures are available. So to know that whether it's a soft magnetic material or it can be a hard magnetic material, we work on magnetic high entropy alloys. And this accelerated development is even more important in case of high entropy alloys, as it contains multiple principal elements. There's a lot of possibilities here that by using conventional method, it's difficult to explore only if we have few composition only. So there are many new high entropy alloys with excellent magnetic properties are likely to be discovered. So using the same technique, here we have used only two powder feeder. In one we use the aluminum, cobalt, iron, nickel, and the other one we use aluminum, chromium, iron, nickel, and printed a cylindrical type of sample. Here the composition across the gradient and X-ray diffraction patterns for these high entropy alloys, and you can see that there is a continuous change in the cobalt and chromium, one side to when we go one side to the other side. So below we have aluminum, cobalt, iron, nickel, and at top we have aluminum, chromium, iron, nickel. And all these samples in XRD show some B2 ordering along with the BCC. So we assume that there are some one ordered phase at least in these samples, and possibly some mixed phase of ordered and disordered. These are the back-scattered SEM microstructures for all these samples. So x equal to 1, 0.8, 0.6 to x equal to 0.4. So x equal to 0. So you see all these microstructures, so they are equax grains. But for x equal to 0.8 and x equal to 0.4, there is some precipitate phase at the grain boundary. So to know about this, that what is that, we have investigated these samples for TEM within the transmission electron microscopy and found that this grain boundary phase is basically phase-centered cubic. And by SAED, it was confirmed that it is a disordered FCC phase. And we also measured the composition across the grain boundary. So this FCC phase is having more iron and cobalt and less aluminum. So here is the atom probe tomography results for x equal to 1 composition to see the atomic scale, what's happening, is there any partitioning or not. So we found that by using EDX and all, it was very, very homogeneous and all, but in nanoscale level, there is some partitioning that if we see here in one side, we have more iron, cobalt, and another side, we have nickel and aluminum. So this we are trying to use this thing to understand how we can make a material with low cohesivity and high strength by doing some Lorentz microscopy studies. So this work is on the way. This is the magnetic properties for these aluminum, cobalt, chromium, iron, nickel. So we see the saturation magnetization increase with increasing the cobalt content. However, the cohesivity first increase and then decrease. We also measure the Curie temperature for this, and Curie temperature is also, at one side we have less than 400, while the another side Curie temperature change is more than 900. Interestingly, this was measured using magnetization versus temperature. So basically, Curie temperature is nothing but when the magnetization becomes 0. So that we see the Curie temperature. So these two composition, x equal to 0.8 and 0.4, is having a second kink here. This is we identify is because of the grain boundary phase available in this sample. So the magnetization behavior of magnetic high entropy alloy systems open possibilities to tune these alloys for specific applications. We can use it for high temperature applications. We can use it for medium temperature applications. So here I summarize my first part of my talk. So we have developed iron, nickel, vanadium, iron, cobalt, nickel, and magnetic high entropy alloy using lens processing technique. Lens process parameter used to control the crystal structure and magnetic properties. So the combinatorial approach to materials development via additive manufacturing has been demonstrated. For the case of graded iron cobalt, significant reduction in cohesivity after heat treatment was observed, and we identified the best combination of magnetic and mechanical properties. In the case of iron nickel, the saturation magnetization decreasing the nickel content, and the cohesivity also decreased with the nickel addition. For the case of ternary system, iron, cobalt, nickel, we identified iron 7.4 cobalt, 11.3 nickel, which show that an optimum magnetic and mechanical properties. For the case of high entropy alloy, saturation magnetization and Curie temperature rise monotonically on cobalt addition. So additive manufacturing is an excellent approach to develop a magnetic component with value-added architecture. Let's move to the second part of my talk, which is on magnetic cooling. First, talk about why we need a magnetic cooling. There are many sources of waste heat energy and waste heat. For example, in United States, lots of energy is unutilized. In the case of UK, also here you can see that there is a significant amount of heat released at different temperature level. We have a heat release at less than 100, between 100 to 200 and 200 to 300. Here you see a list of industry where we use the waste heat sources, for example, data center, electronic board, solar panel. And of course, we all know that there is always waste heat in heat engine in consequence of the thermodynamics law. So for that, in addition to waste heat, this also reduces the device efficiency and service life. So focus here is low and medium waste heat recovery. So there are many methods which are conventionally employed to remove the waste heat, but these methods have their own limitations. For example, they use the pump and fan, water evaporation, and required a high maintenance. So we need a better technique to for the cooling. And the solution can be a magnetic cooling. The thermomagnetic cooling is just same as similar to the natural convection, but it utilizes the field gradient in addition to the temperature gradient. So this technique is basically no pump and fan are required for this. There is no maintenance and no vibration and no edge. So thermomagnetic convection is can effectively cool the heat load. So as the medium and to carry and remove the waste heat, we use the ferrofluid. And ferrofluid is nothing but is dispersion of magnetic nanoparticle in a medium, and that medium can be either water or it can be oil. The condition is that the particle size should be in nanometer range. So we have prepared this ferrofluid for MNZ and ferrite base, and later we also work on only for ferrite-based ferrofluid in oil. So this is the very first image pictures what when we developed this cell pumping magnetic cooling. Here you see this is a circular tube filled with ferrofluid, and here we have a heat load, and this is a permanent magnet which can employ a field of 0.3 Tesla, and this is heat sink and some temperature logger to measure the temperature. So when we apply the magnetic field, ferrofluid start to circulate, and the heat from this heat source transferred to the heat sink. So cooling without any moving mechanical part. Here is a, you will see that, let's say this is a cold ferrofluid here, and this is heat load, heat sink, and because of this heat load, this ferrofluid become hot, and when we apply the magnetic field, so this cold ferrofluid is attracted by the magnet. At the same time, the hot ferrofluid doesn't have any interaction with the magnet because you know that after certain temperature it go to its Curie temperature. So now, because of this thermomagnetic effect, it circulates spontaneously. So using this temperature difference and magnetic field difference, the ferrofluid circulate. These are the simulated results here. The first window is showing the heat load, heat sink without a magnetic field. And you can see that the heat is only at the high temperature at this region and low temperature at this region. But when we apply the magnetic field, it starts to circulate and transfer heat from here to heat sink. So magnetic field plus thermal field drive the ferrofluid and cool the system. Here are the results. So for that, what we do, we first measure the temperature without magnetic field. So let's say here, without magnetic field, the temperature was 64 degrees centigrade, and then we applied the magnetic field in starting. Then the temperature could not reach more than around 48 or 47. So this difference is that we are heat from heat load to heat sink. And good thing here is that when we increase the initial temperature, let's say here it was 64 and then 74 and then 87, the difference increased. So this window is the temperature difference and with the initial temperature. So it increased from around 16 to 21. So the cooling with increasing the initial temperature. So that gives us the feeling that it's an automatic kind of system. So cell pumping, magnetic cooling, we see the effect of magnetic field here. So the black curve here showing the without magnetic field. And then we apply 0.2 Tesla, 0.3 Tesla, 0.25 Tesla, and 0.3 Tesla. For this study, we gave a constant, the maximum field we applied only up to 0.3 Tesla. And then, yes, we found that with increasing the field, the cooling increased. Next, we checked the switching effect. And what is the switching effect? Switching effect is that we first haven't applied the magnetic field, and system we check the temperature, heat load, and in between, after let's say 20 minutes, we apply the magnetic field. And immediately when we apply the field within 2-3 minutes, it cool, significant cooling. And when we again remove the field, it go to the same position, and it show the cycle cyclic behavior. We did this kind of experiment for different temperature and found the same here also, that the cooling increase with the increasing the initial temperature, and it's a completely cyclic behavior. So here now, the next is we wanted to check whether this technique is applicable only for below room temperature, below 100 degree centigrade applications, or it can be utilized for kilowatt level of heat load cooling. And also we tried the long distance heat transfer using this technique. So for kilowatt level heat loading, we made a device which has a multi-torus. And here are the results. So we found the similar behavior, but with a huge temperature difference. For example, at 0.5 kilowatt, and the cooling was 148 degrees centigrade, and when we increase it, it changed to the 155, 193, and 214 degrees centigrade at heat load of 1 kilowatt. So we found a better cooling with increasing the power, and so this give the device is self-regulated. If you increase the temperature, it will cool fast. Here is the very recent results. We are trying for the long distance heat transfer, and this here is my fellow is working here, and this is 8-meter long magnetic cooling devices from one corner to the room to another corner, and we were able to get the cooling for such long device also more than 40 degrees centigrade. So here the summary for the second half of the talk. So the cell pumping magnetic cooling prototypes were developed. The effect of magnetic field initial temperature have been studied experimentally and by simulation in COMSOL multiphysics. I say that it's the first generation because I started work with that. And so in first generation, which is where we use the maximum heat load below 100 degrees centigrade and use the magnetic field of 0.3 Tesla, results a temperature drop of 28 degrees centigrade. In second generation, where we utilize this technique for kilowatt level, we applied a little higher magnetic field, 0.4 Tesla, and the temperature drop of 214 degrees centigrade was observed. Third generation, on which we are working on, we prepared a device on 8-meter long, where we fixed the maximum temperature 197, and we achieved a cooling of 41 degrees centigrade. So the thermomagnetic cooling is self-regulated, and cooling increase with increasing the temperature. So let me acknowledge my colleagues and collaborators who made this work really possible. Raju V. Ramanujan at Nanyang Technological University, Singapore, Professor Rajrishi Banerjee at University of North Texas, United States, Dr. Stephen Gorsey, University of Bordeaux, France, and funding agencies A-Star Singapore, National Research Foundation Singapore, Create Singapore, and Air Force, US Air Force. Thank you very much for your kind attention. Please feel free to ask the questions.
Thank you so much, sir, for your outstanding presentation. It was a delightful learning experience for all of us to discover something new about this domain. I hope all the participants will be benefited from the knowledge you shared with us. So with your permission, sir, if you would like to take few questions from the participants.
Sure.
Participants on MS Teams may raise their hands to speak, or they may drop their questions in the comment section of our Facebook and YouTube pages. Those who are here in MS Teams, please raise their hand and speak to our speaker.
Yes, first question from Syed Abdur Rahman.
Yes, please.
Hello, sir. Sir, just as a combination of mechanical and magnetic properties are important, how important is a high temperature magnetic properties for materials, and how far have we succeeded in developing it?
So high temperature applications are, it depends where you are using. For example, let's say if you are using this in transformer, so the Curie temperature up to 300, 400 is okay. Means we can basically all the materials cannot be used for all the applications. So application should be defined based on the material properties. So basically, for example, the material which is iron cobalt based material has high Curie temperature, but the other properties, other magnetic properties are not that good for that. So let's say for aero applications, we need a high temperature material. So for that, we will use iron cobalt type of material, and we'll compromise for, okay, let's have other properties not as good as the Curie temperature. So we, for example, we achieve the Curie temperature up to 700 degree, which is, you can say most of the application, we can utilize this in most of the application. I hope this is the answer of your question.
Yes, thank you, sir. So, and just one more thing, sir. I am very interested in this field of studying functional materials, but at this point of time, my knowledge is not that good when it comes to it. So how should I begin, and where should I begin from? So, like, if I want to go ahead with this field in future.
So functional material, you mean the magnetic material, because functional also, other material also. Yeah, so basically, I think we can start with some basics, basically. Basic in the sense that, for example, for this research, we must know that what are the critical properties are required and how they influence with the processing parameter, with the composition and that. So that kind of thing you can get in some kind of basic textbooks and those, I think. This is not that difficult thing. If you can do the metallurgy, you can definitely do this. This also, it's not some little bit physics involved.
Yes. Thanks a lot, sir.
You're welcome.
Next question from Devopri Banerjee.
Yes, please.
Yes, Devopri Banerjee, unmute yourself. Devopri Banerjee. Okay, next, anyone? Yes, Devopri Banerjee. Okay, anybody having any question?
Hello?
Hello, yes.
Yes, sir, I had a question first, sir. Like, how does the defects of the material affect the magnetic properties for both especially for super alloys or any other magnetic properties, for any other materials?
Yes, very good question. So defects, yes, that's the region that it's challenging to have this high strength and low cohesivity material. So if our system is having more defects, that it's very difficult to get a good saturation, good magnetic property. Basically, for example, let's say this window is, can you see my slide, right?
Yes, it is visible.
Yeah, let's say this window is open here. For example, this saturation magnetization is less dependent on this defects and all. It's mostly depend on the composition, means basic magnetic movement of the element inside the material. For example, it has iron and cobalt, and it's known that when we add the more iron, that the saturation magnetization will increase. But this behavior for the cohesivity is because of some stress developed in the materials, some kind of defects inside the material. And this is a kind of open challenge to know that how much defects can get the more cohesivity or less cohesivity. This is like this. Is this the answer of your question, or question was different? Hello?
Hello. Yes, I understood something like, yes, sir.
The next question from Subhadip Paul.
Hello, sir.
Hello, yeah.
Hello, sir. Basically, magnetic materials are used for the drug delivery cases. So, how to make the magnetic materials much more compatible to the body in case of drug delivery? Because it is one of the emerging research area in the medical field. So, how to make it biocompatible?
Okay. So this is something for drug delivery and hyperthermia kind of applications. Ferrite-based particles, Fe3O4, are the most usable particles. They can easily use in the human body. There is no harm to use those particles. However, they have some limitations. So pupils are trying other materials. For example, this iron cobalt cannot be tried in the human body. It's very, very harmful. But for the iron oxide, they are approved by FDA, USA FDA. So it can be used. And in some cases, we can coat the materials for a little coating on the particles on the top, which can decrease the toxicity of the material. So the existing best material for hyperthermia and drug delivery is the iron oxide. Even this iron oxide is in every human life. We have this in our body. Our mind contains some iron oxide nanoparticles. So that's the reason this is already approved, and some people in Europe are already trying to use it for real application.
Sir, yes, sir. Basically, if the iron oxide, then basically within our body, the iron content is some proportion is there.
Yes.
Your question is not audible.
Sir, basically
within
our body there is a percentage of iron content. But if the iron oxide is used, then there will be the fluctuation in the iron content, and it may also cause a disease. So during that part, how we have to think that this portion can be used, and how this can be diminished, this to maintain the balance.
Yes, so that's the reason. It's not advised to use the huge amount of. So we only use the very limited amount, and then we try when we deliver the drugs, right? So it's something that drug will be delivered to the tumor, and then the particles will be inside the body. So that's the reason we don't use much, and this is one of the reasons it's not fully functionalized yet. So basically, I would say that it is not an easy task to get rid for this problem, because iron oxide is the best material, and I would say that it's very difficult to get another replacement for this material. The only thing is we coat it and little bit we can. Some people are using, for example, a gadolinium nanoparticles coated with again iron oxide, because gadolinium is even more toxic than iron oxide. But they are saying that by coating that we can decrease the toxicity, and iron oxide is good for not that harmful at the gadolinium.
Okay, sir. Thank you, sir.
You're welcome.
The next question from Arjun. Unmute yourself. Arjun R.
So I already asked. Sorry.
Okay. Any question from social media platform? YouTube, Facebook live page? Who are responsible for handling YouTube and Facebook live? If you have any question in the chat box, you can directly ask. Then if there is no any question, we'll move to the next part.
I have a question, Dr. Varun. I have a question.
Yes, sir. Yes, sir.
You are talking about the ferrofluid, right?
Yes, sir.
So what method you have prepared those ferrofluid? Means is it by two-step method?
So it's a chemical method.
Yeah.
So from the talk you may understand. So we have 3 generations. So for first generation we used our ferrofluid, means we homemade ferrofluid. We prepared it in laboratory, which is MnZn ferrite particles. So we first synthesized the MnZn ferrite particles using the co-precipitation method. So that method gives us the particle size in the range of 8 to 15 nanometer in this range. And then those particles were coated. Because the first requirement here is that the particles should not be away when we apply the magnetic field. It should be very homogeneous dispersion. So that's the way we use for ferrofluid preparation. Let me go to the slide. Can you see the slide?
Yes.
Yeah. So this is the first part is to prepare the particles and then coat it with oleic acid. And then we use the ammonium hydroxide, some string for 80 degrees centigrade. Then these particles are coated with the oleic acid, and then we disperse into the water. So the thing, this image is relatively.
Oleic acid, is it the stabilizer used? Oleic acid.
Oleic acid with ammonium hydroxide. Yes, sir.
Okay, so that is a stabilizer, right?
Yes, sir. Yes. So okay, basically, then, if we just disperse the iron oxide in water, they will just sit down. They will not
you have done some vibration, magnetic stirring, and sonication. These things you have done mechanically.
We did the stirring for mechanical string here because magnetic couldn't work because of magnetic particles. So we did the mechanical thing using some non-magnetic stick there. So I would see this. I think let me enlarge this. So if you see this image, the complete liquid behave like a magnet when we put it near to the magnet. So this is the proof that it become a ferrofluid. But if it's not properly homogeneously mixed and coated, then what happen? The particles go here and liquid not move with that.
Does it give some enhancement in thermal property, thermal conductivity? So I know the nanofluids are used primarily for enhanced thermal conductivity. So does the ferrofluid also give some enhancement in thermal conductivity?
Thermal property, definitely it's enhancement. Yes. However, they are oxide nanoparticles. So our next goal is something to prepare the ferrofluid for metallic nanoparticles so that we can further improve this thermal properties for this ferrofluid. But yes. We are trying. There is no success because the metallic particles have very high density. So once we apply the magnetic field, the particles go away from the liquid basically. So for that we tried many coating and all, but there is no success on that side.
Okay, so that metallic particles should have magnetic property as well as thermal. It should give high thermal conductivity. So both
yes.
are interesting.
Both are useful. Yes.
Okay. Thank you.
You're welcome.
Yes. Last question from Devapriya Banerjee.
Good evening, sir.
Yes. Good evening.
Good evening, sir. Actually, I was facing some technical glitch because of which I was not able to contact you the very first time. Anyways, I'm sorry for that. The thing, sir, I want to know about this particular thing that you said. There are two questions. Number one, the lens. When we are working with this lens application, the lens, you
Yes,
said that at particular composition, every time we want to alter a composition, we can alter it by at each layer. Each time the layer is going, we can alter the composition. Now the question is, can we characterize it or not?
No. That's the reason I mentioned that in
Yes, sir.
principle, it's possible to have every single layer for one composition, but in the lab practice and what we do, we print few layers for one composition and then change the composition. So basically, all the techniques, available techniques.
Typically, we can make a layer. Yes, sir.
Yes, we can make, but we cannot characterize. So this slide, I think I haven't showed during my presentation here, that we try to use the high throughput characterization in addition to the high throughput material synthesis. So for example, the XRD what we have, it can easily detect 1 millimeter change in the composition. But if the change in within 1 millimeter, it cannot. In the same case for the XRF also. So we don't, so it's very difficult. That's why I was saying that, yeah.
And one more question I need to ask, sir. Like at the time of that implementation of the laser on that particular surface, by changing the can we change the intensity of the laser? And if yes, we can change the intensity, will it affect the magnetic property of that magnetic material? Like the thing which we have, can we alter its magnetic property by changing the intensity of the laser?
Yes, of course. So see, this particular, so basically it changed the structure. So for example, if you see here we did the same. Means we changed, in starting we used the laser power 300 watt and some particular travel speed, 5 inch per minute. So if you compare that, your question is on the power. If you compare with this, where we have this travel speed same, this and this, right? This one is the 300 watt and this one is the 500 watt. So here we have a pure HCC phase. Here we have a HCC plus little bit BCC phase. So using the power, we can change the property. If it changing here, this crystal structure, it also change the magnetic property, drastically change. See, FCC is having 120 EMU per gram saturation magnetization, and BCC is having 165. That's why we started work first to optimize the process parameter according to the requirement. So there are many process parameter here. One another thing, what maybe in your interest, to get a high density, we need the high laser, high energy. But if we increase too high, then we can get some cracks inside the sample. So the optimization is required basically.
So that does mean that even if we are gaining a lot amount of magnetic property, we are not sure about the mechanical property by doing this alteration in the power.
Yes, so that's why we have to optimize both together. Yes. So it's possible that, okay, we got a very good magnetic property, but samples are having cracks. That means they are not mechanically strong, so we cannot use for the application. So we'd have to compromise and then optimize the thing.
Okay, sir. That means both of these are mutually exclusive.
Exactly.
Okay, sir. Okay. Thank you, sir. That's it from my side.
Thank you, sir. Next, I'll request Ravin to proceed.
Thank you, sir. Thank you for clearing out all the participants with so much dedication and tenderness. I hope it will help them to work in their field further. Coming to an end of the technical session, I would request Mr. Syed Abdur Rahman, President of IIM NIT Durgapur student, to give the vote of thanks to our renowned guest and speaker of today's talk.
Thank you. Thank you very much.
Thank you, Robin. My to all, I, on behalf of IIM Students Chapter NIT Durgapur, would like to extend my heartiest gratitude to Dr. Varun Chaudhury. Thank you so much, sir, for your talk today, and thank you for all the motivation. We hope to have many more interactions with you in future too. I would also like to thank Dr. Madan Mohan Ghosh, HOD of MME Department, and Dr. Arup Kumar Mondal, our faculty advisor, for their continued support. I would also take this opportunity to congratulate all the members of the organizing committee for making the event possible, despite all the challenges. Last but not the least, a big thank you to all our guest attendees and my fellow classmates for being a part of this event today. Thank you so much, sir. Thank you so much.
Thank you. Thank you. So if you have any other additional questions, my email is on the first page of the slide. Please don't hesitate to ask, and not for this particular question, any issue. If you want to know more about the Singapore, and then so please,
sure.
Yeah.
So I will share your email to them. Okay.
Sure, sir. No problem.
Okay. Thank you, Dr. Varun, for being with us for some time. We have spent a wonderful time with you. Thank you.
Thank you very much, sir. I'll be in touch with you, all of you.
Yeah, sure. Bye. Bye.
Bye-bye.
Thank you, sir.